Okay, so starting from usual roadmap, last Monday we started talking about more modern approaches to learning-based control. Specifically, we looked at imitation learning as our specific paradigm of interest, where, loosely speaking, we pitched imitation learning as this idea of wanting to learn from demonstrations. And so we saw different types of ways of doing this, specifically behavior cloning and inverse reinforcement learning, where the idea there is that we want to directly learn a policy that represents or mimics and approximates the behavior of our expert, or do we want to learn the objective, that is the underlying reward function that the expert is optimizing. However, we also recognized how imitation learning techniques at their core are essentially kind of capped in terms of performance by the performance of the expert demonstrations. And so for today and for the rest of this class, we move towards reinforcement learning, which on the other hand is this idea of wanting to learn from interactions as a basically paradigm to learn through trial and error and discover solutions for optimal control problems. So today and for the next two classes, we'll be looking at model-free reinforcement learning, and then we'll be looking at model-based reinforcement learning. And specifically for today, we'll start with a brief recap of the reinforcement learning problem setting, and we'll dive a little bit deeper into what I'm referring to here as exact methods. So if you recall, in our lectures on dynamic programming, we discussed value iteration and policy iterations as ways of solving Markov decision processes. And so we'll look a little bit more closely on those. That is methods that leverage dynamic programming for computing as solutions. The reason why I refer to them as exact methods is because implicitly these methods, that is value iteration and policy iteration, were leveraging the fact that we knew the underlying dynamics of our system, which is something that, on the other hand, we assume we won't have throughout reinforcement learning. And this is where learning from interaction will come in place. And so from that, we'll then leverage and kind of build upon those techniques to introduce two, I would say, really fundamental kind of approaches for model-free learning, that is learning from interactions. Specifically, we'll look at Monte Carlo learning and temporal difference learning. And then we will wrap up the discussion with some kind of concluding remarks and kind of as a segue into the next few lectures, where we'll be diving more closely into specific algorithms, both model-free and model-based. And so starting from our problem setting, we introduced in the past kind of this idea of a Markov decision process, where ultimately an MDP is represented by a quintuple of elements, here defined by the calligraphic M. Loosely speaking, we have an action and a state space, which represent the possible set of states and actions our agent could either be in or could enact. We have a transition function, which is represented in the RL literature usually as a distribution over next states, given states and controls. We have a reward function, which maps states and controls to a scalar measure of success. And we have a discount factor, which is just a scalar between 0 and 1. We discussed this, how this is both useful from an intuitive standpoint. It kind of trades off long-term reward with respect to short-term reward, but also as a mathematical object that enables an infinite sum to become tractable. Where does this infinite sum come in place? It comes in place from the overall goal that we want to maximize when we talk about Markov decision processes. That is, we want to find the optimal policy pi star that maximizes the expected cumulative discounted reward over time. And to solve these problems, last time we introduced the concepts of value functions and Bellman equations. Specifically, we introduced the state value function, represented as V, as essentially an element that encodes kind of the expected reward that we can expect to have starting from some state xt, and then following a given policy pi. So the value function is an object that depends on a policy. And we saw how these value functions satisfied some fixed point equations, namely the Bellman equations. And so we discussed the Bellman optimality equation, which relates with the optimal value function V star, which essentially says that the optimal value function V star at some state xt is essentially equal to the maximization over controls ut of the sum of the instantaneous reward plus the expected value at the next state xt plus 1 where the expectation is essentially averaging out over possible next states. We saw how this is a property of the optimal value function, but we discussed this how a similar fixed point equation holds also for any policy pi, where very similarly, this fixed point equation, that is the Bellman expectation equations, is defined as we introduced also a couple of weeks back. We did a very similar discussion for the Q function, that is essentially a measure to represent our expected future reward, starting from some state xt, taking an action ut, and then following a given policy pi. Again, very similarly, here we have some fixed points equations which these concepts satisfy, which are namely the Bellman optimality equation and expectation equation for the Q function, respectively. Why did we introduce the Q function? We introduced it because from the perspective of developing an optimal policy, this is pretty useful in practice because it allows us to define a policy implicitly through the Q function as the argmax over U of the Q function defined on some state x. And so very practically, at least for the perspective of tabular methods, that is the one we'll be looking at today, so where we don't discuss function approximation, I think it's useful to visualize value functions, both state value functions and Q functions, as just look at tables. So the value function v of x, you can namely visualize it as the value for any specific state, x1 to xn, assuming we have n possible states. And very similarly for the Q function, this would then be a matrix representing possible Q values for all states and all controls. Okay, so we said how these were essentially interesting properties that derived from this infinite horizon Markov decision process problem setting. And we then operationalized these concepts into practical algorithms, specifically through, as we were saying before, value iteration and policy iteration. And in these algorithms, they essentially boil down, if you remember, as mechanisms where we iteratively enforced these fixed points equations until convergence. So in value iteration, we recursively enforced the Bellman optimality equation until we converge to the optimal value function. And for policy iteration, we alternated between a step, which we call the policy evaluation step, that is the application of the Bellman expectation equation, as we were trying to estimate the value of a given policy. And then we had a policy improvement step, which turned out to be a greedy policy improvement in our case. So long story short, we have seen all of these objects before, and in the past we derived actionable algorithms to solve macro decision processes by basically enforcing these Bellman equations. But in order to do this, we always leveraged the knowledge of the dynamics function. So looking a little bit more closely at policy iteration, because this will be a concept we'll be building on today. If you recall, policy iteration is essentially an iterative algorithm where we are given an initial policy pi. And for every iteration k, that ranges from 1 until some convergence or termination criteria is met, we're basically alternating between these two processes, which visually we could visualize here on the slide. We have a given initial guess for our value function and a given initial policy. And we alternate between the policy evaluation step, which basically evaluates the value function for that policy. And then we have a policy improvement step, which on the other hand uses the most recent estimate of the value function to derive a better policy from that. How did these two processes look in practice? For the policy evaluation step, we recursively enforced the Bellman expectation equation, as we defined before. And for the policy improvement step, we were basically taking the argmax over U. Yeah, so note again that in both of these formulations, we're leveraging the fact that we have the knowledge of the dynamics function. So more concretely, let us look at how this looks from an implementation perspective in practice. Let's consider this grid world example where we have this basically 16-dimensional world where we could be in either of these grid cells. We have 14 non-terminal states, that is the white cells, and we have 2 terminal states or goal states that we want to reach. So loosely speaking, the goal here is will be spawned in any of these cells, and the goal is to get to the goal terminal cells as fast as possible. How do we encode this objective of getting to the goal point as fast as possible? An idea could be to just fix the reward to be -1 or any negative number until we reach the terminal set, the terminal cell. In this case, we're assuming we can take kind of these 4 possible controls, so the 4 cardinal directions. And if we take some of a control that would lead us out of this grid cell, we just stay where we are. We're doing this assumption. And for simplicity of calculation, we are assuming that we have an undiscounted MDP, so where gamma is equal to 1. So in practice, let us take like a first step in the policy iteration algorithm. Right? So we say that we have a given initial policy, and for now, for simplicity, since we have potentially no clue about what a good policy is, we just assume that our policy is a random policy. So in all states, we just take a random action with equal probability. Again, we have potentially no clue of how to initialize the value function, so we might just initialize it as all zeros. So here on the left column, you're basically seeing different iterations of the policy evaluation step. So we are enforcing the Bellman expectation equations at k equals 1, k equals 2, until we converge. So concretely, say we are at this grid cell over here, so the coordinate 2, 2. What we're doing there is that we're updating the value at that specific state as the current estimate of our value function. So the reward, sorry, plus the expected future values in the next states that we would expect to be in. So more formally, we have this -1, which is just the reward of taking one step. And then we have the expectation of all possible next states, which in our case are equally distributed around the 4 possible neighboring states. So we'll be looking at xt plus 1 in 1, 2, 2, 1, 3, 2, and 2, 3. Right? So we are looking at wanting to update this cell over here. So the reward of taking any move is -1. And then we have to take the expected value of the next state that we land in, which is, in our case, one of these 4 states. So, and where we take the expectation under our transition dynamics. This probability of being xt plus 1 given xt and the action that we would take in xt times the value, the previous estimate of the value function. So this is v1, if you wish, and this would be v0 in that state. Right, so here, nothing too fancy, I just basically formalized what we are writing, the Bellman expectation equation. Yes?
Is it kind of just convention that at k equals 0 you have all zeros rather than just initializing with the value, or rather with the reward for each state?
There is just a choice. So if you have knowledge in general, knowledge in your problem that you wish to encode as a starting point, then it's definitely a good idea to do so, because it just speeds up the convergence. Okay. But in this case, we just assume we have no knowledge whatsoever, and we start from all zeros. So in this case, well, we know that our previous guess was all zeros, so this is always 0. In theory, we would know that this is equally distributed across our 4 steps, so this would be always 0.25. But in general, since we have a 0 term here, this cancels out. And so for all the grid cells in k equals 1, we would actually get -1. And you can then imagine that if we repeat this process across iterations, we basically get an evolving surface of our value function. And if we do this until convergence, we would then get something that looks like this. So at this point in our algorithm, essentially we have taken, kind of again visualizing it here in our sketch, we basically took one step in the policy evaluation step, right? So we concluded a full policy evaluation step where, given a policy, we estimated the value for that policy. What is the next step then here? According to the policy iteration algorithm. Yes?
We want to use those expected values to derive a different policy.
Yeah, exactly. So we want to then basically do this step, which is the policy improvement step. How did we define it so far? We basically take this argmax over this quantity over here, right? And which essentially means that say that we converge to this value function over here, the policy that maximizes this value function, since the reward is always -1 no matter what we do, the policy will basically converge to taking the action U, which leads to the best, the state with the best value function value, right? So from here, we could immediately, like even visually see that in each of these grid cells, we're basically, the policy that we get from that policy improvement step essentially would be pointing towards the state with the neighboring state with the best value function. Right? Which is exactly what we get here. So this would be the visualization of the policy that we get out of the policy improvement step from this value function which we estimated before. Now, of course, if you kind of, in general, we run a full policy evaluation step until convergence in this case. But you can always hypothesize doing the policy improvement step at intermediate steps in our policy evaluation iterations, right? In this case, since this is a very simple problem, you would actually get the optimal policy even if you stopped before convergence. But this is not guaranteed to be the case in general. For example, here, right? If we stopped immediately and did the policy improvement step here, we will get a policy that is still slightly better from the original one, because we do get some nice behavior here, where we're not random anymore, but still not there yet. Yes?
Is a stationary policy enough of a signal to say that you've converged, or is it possible that between iterations you could have the policy not change, but then if you continue and the value function continues changing, you then might update the policy later on?
Mm-hmm. Yeah, so in general, like I guess the question is, how do you define termination criterion for this case? So in general, for these tabular settings where we can actually enumerate all the possible value functions, so values for each states and each state action pairs, this is proven to converge. So there is no, like if you run this long enough, you will be converging. In general, there are different types of termination criteria you could come up with. Some could be like delta-based, so depending on how much it changes across iterations. And there is no real kind of one best rule for doing that, if that makes sense. So to answer to your question, in this case, as long as you run it long enough, you will be converging to the optimal value function and policy. Okay, and so you will notice also running through this example that all of these formulations, in this case we looked at policy iteration, but the same thing holds for value iteration. All of these formulations require a model of the MDP. So we use the transition dynamics to update our quantities. In general, to solve unknown MDPs, that is MDPs where we don't have access to the ground truth transition dynamics, we'll use interactions with the environment to replace this knowledge. And so, more generally speaking, we the main limitations of these exact methods, such as policy and value iterations, are mainly two. The first one is that the update equations require access to the dynamics, and we'll use sampling-based approximations to basically solve and address this challenge. And we'll see this more shortly. And the other one is that kind of iteration over and storage of all of the states and actions and the values for the states and actions can require extremely kind of a large memory effort. And also it could just lead to very long kind of faraway convergence for these algorithms. And so whenever we have a very large state action space, we'll see how function approximation could come in handy. Today, we'll be mostly looking at sampling-based approximations, but starting from next week, we'll also be looking at function approximation. Okay, any questions here before we get started with the first algorithms? Okay, so let's start from Monte Carlo learning. And the idea of Monte Carlo is actually extremely simple. So we're saying that we are interested in estimating these values for value functions in general. And we want to do this using samples. What do we mean with samples in our case? So we have an environment which we assume we can interact with. And interactions essentially means collecting rollouts, right? So we will be releasing our policy in the environment and collecting the rollouts that we get from the environment, right? So this means collecting a sequence of states and controls over time until we reach some termination criteria here. Now, in principle, what we are interested in when we talk about, in this case, for example, the value of state x1, would be to basically approximate the expected future rewards that I would expect to have if we were able to simulate infinitely many scenarios, right? I'm interested in the ground truth expectation of this value function. To do this, so far, we've leveraged knowledge of the transition dynamics, but in general, this is not possible, right? So we want to do this through sampling. And this means that in Monte Carlo, what we do is that we basically want to approximate this expected value function or expected future reward through the return. The return for us, let's remember that it's just or at least the return of a trajectory, in this case, at time t, is just the sum of all the rewards that we observed from time t onwards. Again, simply put, the return starting from x1 would just be having our trajectory, evaluating all of the rewards that we got over time, and summing them up. And the idea is that if we were to repeat this multiple times, so we don't have only one trajectory, but we have multiple, we would be essentially able to approximate this ground truth expectation that we are interested in through the mean, the empirical mean, essentially. Does this make sense? Yes, and so because of this, essentially Monte Carlo methods are methods that directly learn from episodes of experience, and it is model-free, right? So there is no knowledge of the transitions that we're using here. We're just using interactions or samples from our environment to approximate these values. One caveat, of course, which is also a pretty important one, is that because of how we define the return, which is literally the sum of all the rewards that we observe throughout our trajectory, Monte Carlo methods apply only to episodic MDPs. So there needs to be a termination of our episode at some point, simply because otherwise we will be continuing to summing up rewards forever, essentially. So how do we use this in practice? Kind of an immediate thought there would be to use Monte Carlo methods for learning the state value function V, right? So recall that we defined the return as just a discounted sum of future rewards from given a trajectory. In principle, we are interested in approximating this expectation here, which is just our value function. So for us, the value function is the expected future reward that I expect to have starting in xt following a policy pi. And if you look at this inner term here, this is nothing else than the return itself, right? So the definition of the value function is actually the expectation of the return given state xt. And so with Monte Carlo methods, we essentially, or specifically with Monte Carlo policy evaluation, what we would be doing is that we use the empirical mean to estimate this expectation instead of computing exactly this expectation through the knowledge of the dynamics. Okay, in practice, you could have two variants of Monte Carlo methods. The first is referred to as first visit Monte Carlo, where in order to evaluate the value function at a given state, we would be essentially computing these mean returns only the first time we visit a specific state in an episode. So in practice, once we visit a specific state x, we would be incrementing the counter of how many times we visited that state x. We would be incrementing the total return, so that is all the returns that we ever saw when visiting that state x, and then just taking the mean. And in general, assuming we have, the more samples of this trajectory we would have, so if with n going to infinity, we would be converging to the ground truth expectation. The other approach is the every visit approach, where now we account explicitly for the situation where maybe within our rollout, for some reason, we are maybe visiting kind of state x1 again, right? So we are maybe taking some detour and we end up in the starting state again. In the first visit, we would basically be ignoring the return from the second visit onwards. In the every visit, we just consider these two as independent visits and update the mean regardless. Again, this is just a kind of technicality when you look at implementation, but the overall idea is that we want to approximate these expected future rewards. Because we cannot compute these expectations exactly, we approximate them through an empirical mean. Yes?
Same state over and over again from different trajectories, isn't it? Wouldn't it be, I don't know if unfair is the right word, but to exclude that from your database with the first visit mentality rather than doing the every visit mentality? Mm-hmm.
Yes, I think it's a valid point, especially if you have these maybe degenerate cases where the policy is visiting the state over and over. I would say in general this probably boils down to you want to have sufficient exploration, right? So you want a policy that basically explores your state action space well enough for these tools to be efficient and effective in practice. But yes, so when you have these cases, it is a valid discussion to consider, like, should I go for an every visit example or a first visit case? Maybe in that case, the first visit is what you want. Yeah.
If you're saying this would be used in a model for a case, can you explain an example in practice that you would use this for? If you're not able to run this and collect this data on simulations based on some model that you have, wouldn't it be difficult in practice to set up some experiment and collect all this data?
Yeah, so yes, this is a good question, because in general, so here when we talk about model free, we refer to the fact that we're not leveraging a known model of the dynamics within our calculations. Now, you could indirectly use it by having interactions with the simulator. But in general here, this is agnostic to any kind of environment and reality we are interacting with, right? So by model free here, we just mean that we are modifying all of our update equations, say in the policy iteration case, to avoid using an analytical expression of the transition dynamics. So in practice, I would say leveraging a simulator here would be a concrete example of using this. So we have some simulator that simulates our environment, say a driving simulator, and then we want to use these tools to estimate a value function within that simulated world. But we're doing this without leveraging the potentially extremely complex model that runs under the hood in the simulation, if that makes sense. Yes, does it clarify? Yeah, so bottom line is model free here just refers to the fact that we're not using the transition dynamics. Okay, so let's look at an example. So here, consider the game of blackjack, which we're probably most of us are familiar with it. But in general, kind of here we are assuming that we have a state where we have, we're dealt 2 cards. We're playing against a dealer that also has 2 cards. The state for us is that we are considering the current sum of the 2 cards that we have in hand. That ranges from 12 to 21. We are also specifically recognizing if the dealer's showing the dealer's showing card. So we have visibility of one of the 2 cards of the dealer. So from ace to 10, and we are specifically having a flag if we have a usable ace or not. So do we have an ace in hand or not? In this case, of course, the goal is to beat the sum of the dealer, essentially having the hand that reaches closer to 21. The way we do this is so we have 2 possible actions, right? So at any point in time, either we stand, so we stop receiving cards and the game terminates, or we hit, that is, we ask for another card without replacement. In this case, the reward for us is that when we stand, so where the game terminates, we get a +1 rewards if our sum of the cards essentially beats the one of the dealer. We have 0 if we have a tie, and we have a negative reward if we lose against the dealer. For the hit, when we actually ask for another cards, we get a negative reward if we go above 21, where the game terminates, and we get 0 otherwise. So in general, we are assuming that we automatically hit if our sum of cards is below 12. This is the only assumption that we have on the transitions. So in this case, we want to consider a given policy. So we are given to us this policy, which basically stands if the sum is greater or equal than 20, and always hits otherwise. And so the goal here is, let's now take this environment with these rules and basically run policy evaluation through Monte Carlo sampling in this environment. Is the setting clear? Nice. So we'll be blackjack experts after this, I guess. So what we're looking at here is, assume we are running policy evaluation for 10,000 episodes or 500,000 episodes. So again, here what we're saying, this would be 1 episode of interaction. We're assuming we are playing 10,000 and 500,000 games with the dealer. And these kind of 3-dimensional landscapes are essentially a visualization of the value function. So here specifically we have 2 axes. One axis is looking at the dealer showing card that ranges from an ace to a 10. We have a player sum, so the sum that we have in hand from 12 to 21. And we have the surface kind of differentiated between when we have a usable ace and when we don't have a usable ace. So this is just our state space, right? If you remember those 3 bullet points. So what we see is, first of all, you see a difference between the column that relates with the 10,000 episodes and the 500,000 episodes in terms of noise, right? So these estimates are definitely more noisy than the ones where we have more episodes. Again, the reality is that here we are approximating these expectations through empirical means, and so the more episodes we have, the more we are converging to the ground truth solution. And to basically maybe understand to gauge your understanding here, let us look at some questions, and some questions for you. So consider specifically the diagrams on the right. So why does the estimated value function jump up for the last two rows here in the back? Yeah.
We're stopped hitting on 20 and 21. We always hit until we get there. Either most of the time we're in a bust, but if we do get there, you're probably going to win. It's through 20 to 21 until you hit.
Yeah, exactly. So we are, we're playing a game with our policy that is given to us, where we only stand if we're 20, 21, and if we do, that's a pretty good hand. So we likely win. So exactly correct. And another question could be, why does the value function drop off for the whole last row on the left, on the other hand? Yeah.
When the dealer has an ace,
yes, so that
they're likely to have a 10 to get home.
Exactly. So, or also just having an ace is a good hand, right? So you can use the ace in different ways, and so that's on average is something where the dealer is well positioned. So in general, of course, you see how kind of the bottom line here is that in policy evaluation, we basically had no information whatsoever on how the game works or any dynamics of this game. We basically leveraged simulation, if you wish, or interactions with the environment to estimate future values of all the states. And what we get is, through this interaction, a complete representation of the value of every possible state that we could find ourselves in this game. And so, given this policy that it's given to us, we have exactly characterized kind of its efficacy in all different states, if that makes sense. And this value function is, to some extent, interpretable, right? Because we can more or less understand it, and it's reasonable. Okay, as a just note, in general, we're talking about, in Monte Carlo, we're leveraging empirical means to approximate expectations. Of course, these episodes will be coming in incrementally, and so it doesn't make sense to recompute the means from scratch or store all the possible rewards that we ever observed. But in practice, we often compute the means incrementally, and so we know that this is standard result that we can compute the mean for a given realization x incrementally through this equation over here, where we're essentially updating the mean as the previous estimate plus basically a step in the direction of the new observation. So this is in general for incremental means. Of course, for us, the mean that we're interested in computing is the expected return, right? The mean return, which for us is our estimate of the value. And so we'll be updating our value, our estimate for the value function as the previous guess plus basically a step in the direction of the new return that we have observed. So this is the exact formulation for the incremental mean. In practice, we'll often see this expressed kind of very similarly to what you would see kind of a gradient descent step update rule, where we could have a varying alpha, basically a scalar that changes how big of a step we're taking in the direction of the update. Okay, any questions on Monte Carlo before we move to TD learning? Okay, so Monte Carlo is one, I would say, really fundamental strategy for model-free learning. TD learning is, I would say, the other bigger player when we talk about model-free learning techniques. And specifically, at a high level, TD learning is a combination of Monte Carlo and dynamic programming approaches. So, like Monte Carlo, TD learning is model-free. So there is no knowledge of the transition dynamics in RNDP. And TD learning also learns from experience, right? So we are replacing this knowledge through interactions with the environment. On the other hand, differing from Monte Carlo, but similarly to dynamic programming, temporal difference learning update estimates of, for example, values based in part on other learned estimates. Essentially, we can update our guess towards a guess without waiting for the final outcome in our episodes. More formally, it is denoted as temporal difference learning and dynamic programming bootstrap. So remember how in dynamic programming, we were essentially saying that we could have a recursive function where the value function for us would be at a state xt would be equal to the immediate return, a reward that we see at xt, plus the discounted future value at the next state, xt. Right? Now, in TD learning, since we cannot compute these expectations exactly, because in order to do this, we would have to have knowledge of our transition dynamics, we use samples to approximate this expectation. So in Monte Carlo, we were using the full trajectory to directly estimate the return. In TD, we are only interested in the one-step update, where we will be updating the value of x1 basically as in the direction of the immediate reward that we see, R1, plus the discounted value at x2 in this case. Right, so we'll be using this same property that we can use our current estimate for the value function to basically approximate all future rewards that we would have observed going forward with the episode. So more concretely, let us look at the specific definition. In Monte Carlo, we said that we want to update our value estimate towards the actual return, GT. Specifically, we take a step, alpha, in the direction of the return. In temporal difference learning, we update the value towards the estimated return, where this estimate is taken using basically dynamic programming ideas, where we take the immediate reward plus the discounted future estimate of our value. And so specifically, we take a step in the direction of this target over here in red. So in general, the reward plus the discounted future value is referred to as the TD target. And the difference between our guess and this TD target is known as the TDF. So in general, you see how temporal difference methods combine the sampling of Monte Carlo, because we're only leveraging interactions with the environment to estimate our values, with the bootstrapping of dynamic programming, because we're updating a guess towards a guess. Yes?
Just a quick recap for the first one, the GFT. Does that mean you have to run a bunch of rollouts at each update step to figure out what the actual return would be?
So here, this is independent of how many rollouts you do. So here we're saying that we want to approximate the actual return, so that is the sum of all future rewards, through sampling. Specifically here, we could take one sample of the return, which just means summing all the rewards that we see over time. Visually, we want to approximate this ground truth expectation over here. And we could do this by just evaluating the empirical returns that we observe over time and taking a mean. Now, GT is just the definition of the return. And so for us, assuming we have one sample, this would be a one sample estimate of the actual expectation. In temporal difference learning, instead of looking at the final return here, we actually look at the one-step estimate of that return, where this estimate is just the instantaneous reward R1 plus the discounted guess of the value here. So in other words, our guess here is just a mechanism to avoid having to run through the entire episode, but approximating what this rest of the return will be at time 2, in this case. Does this clarify? Yeah. Yeah.
Just like, do you have a trajectory and then like do one step for like a segment of the trajectory and you just do like one step?
So in general, so the interaction will always be for full rollouts. So we'll be having full interactions with our environment. But then this is changing how we update our value estimates. In the Monte Carlo case, we update our value estimates looking basically one episode at a time, the full episode. In TD learning, we can actually update our value estimates more often, because this would basically be only one update, if that makes sense, because we only have one return. Here we can update our value function before the episode finishes, potentially, because we just use our guess to do so. Yeah. Potentially. Yeah, so kind of looking at differences more closely, we mentioned how Monte Carlo learning essentially requires episodic MDPs because we need to reach that terminal state at the end. On the other hand, in TD learning, because we are only using our own guess to estimate the values, TD learning can learn before the final outcome, essentially. And so TD learning can potentially learn online after every step, but Monte Carlo must wait until the end of the episode to collect those returns. And so, indeed, TD learning can learn without the final outcome, and so can learn from potentially incomplete sequences, and can potentially work in continuing or non-terminating environments. Or on the other hand, Monte Carlo requires this termination. Does this make sense? Yeah, so I would say really kind of Monte Carlo learning and TD learning are kind of the fundamental mechanisms through which we estimate quantities of interest. Most of the times, these are values and value functions. And that these are really kind of, the foundations over which all modern kind of reinforcement learning algorithms are all built on. Either if these are estimated, are kind of value-based methods or policy optimization methods, as we will see, kind of actor-critic and so forth. All of these tools essentially rely on some approximation of value functions. And when we don't have a knowledge of the transition dynamics, we have to resort to interactions with the environment and leverage tools similar to Monte Carlo and TD learning to do so. Yeah.
The full consideration depends on about like the estimated value function, the next step in like any trajectory, for example. And how could that work in non-terminating environments? Like the way I'm understanding is like we would have to recursively go back from the final state to understand the value at that final state and then work backwards to say external coordinations. So how I think I'm misunderstanding how we would do that update or like get the estimates for the value function.
No, I think you have the right intuition, because basically what you're saying is, I get the point that we're updating our guess towards our next guess, and how this could mechanically work online at each step, even without relying on the final step. But you're saying, at the end of the day, we need to ground some of our estimates on an actual value, right? And I think this is correct, and this is exactly where kind of the discount factor comes into play. Because if we take the extreme version where we are we are at step 500,000 in the future, then here kind of the future values will essentially be very close to 0, and so we will have a way to estimate these value functions that is not exploding to infinity. If that makes sense. Okay, but so we're basically saying we're interested in estimating values and value functions. We introduced these two ways of doing so, Monte Carlo and TD learning. which are essentially estimators of a quantity that we're interested in approximating, right? That is the expected future reward, or the cost to go, the reward to go in this case. So let us look at kind of properties of these two estimators, right? So specifically the bias and variance of these two estimators. So let us take Monte Carlo to start. So we're interested in estimating the true value of our policy. And we're saying that in order to do so, we want to use the return, which is just the discounted sum of all the rewards that we observe. Now, of course, this return is an unbiased estimate of the ground truth value. Again, using an extreme example, if the expectation that we're actually interested in will be the expectation over all possible future evolutions or episodes in our environment, and the return is just a sample from this. If we take an infinite amount of interactions and episodes with our environment, we would be converging to the ground truth expectation, right? So in this sense, this estimator is actually an unbiased estimate. In principle, the true TD target, that is for temporal difference learning, is also an unbiased estimator of the actual value. But this is only if we assume we already know what the true value function is, right? So here we're saying we're using this value function at the next step to basically approximate the future reward. And if the value function is exact, then this would actually be an exact characterization of the expected reward to go. But in reality, we won't be using the true value function, because the purpose of learning is trying to estimate the value function. And so we will actually be using an estimate, right? Kind of a v hat for our value. And so since this estimate won't be exact, we're introducing some bias. Does this make sense? Yeah. Okay, and how about variance? So, in general, the TD target is a much lower variance estimator than the return. And this is because the return depends on a full sequence of random actions, transitions, and the reward realizations. On the other hand, the TD error kind of only depends on one kind of sample of basically stochasticity of a random action, transition, and reward. Right? So here we're saying that in order to approximate the future reward to go, we are either approximating through the return that we evaluate here, or we approximate it through the TD target. So basically, in this case, R1 plus V x1, right? So in the former case, in order to compute the return GT, we're basically sampling multiple times over the episode. Where sampling means we have potentially unknown kind of stochastic transition dynamics that we are repeatedly sampling from. We have a potentially stochastic policy that we're potentially sampling from. And the reward itself might be a stochastic reward, right? On the other hand, for the TD target, we're doing the same sampling, but only once. Right? And so in this sense, the return as an estimate of the true value is actually a much higher variance estimator, because there are just many more possible futures that we are kind of taking into consideration here. Okay, but so let's really kind of drive this message home, and I think it's useful to visualize this through these sort of tree-like diagrams. And specifically, let us look at Monte Carlo first. So we basically introduced what is often referred to as a Monte Carlo backup, meaning the update equation that we use for our value estimates according to Monte Carlo learning. And we define this as updating our guess of the value function by taking a step in the direction of the return. What does this mean visually? In this diagram, kind of white nodes here represent states, and black nodes represent actions, and T represents a terminal state, so that is where the episode terminates. And so you see how potentially in state xt, we could be taking two possible actions. And depending on the action that we take, we could land on potentially two different states. In a Monte Carlo backup, this essentially means that in this possible tree of all kind of futures that we could observe in our environment, we approximate the ground truth expectation of the values by essentially taking a full episode of interactions with the environment until we reach a terminal condition, and using the return that we observe over here to update our guess. Differently, in TD learning, we defined our update as taking a step in the direction of the immediate reward plus a guess of our future values. And so this visually means that rather than having to take a full episode of interaction until reaching a terminal state, we only look at the one-step transition, if that makes sense. On the other extreme, kind of positioning this with respect to what we saw with dynamic programming, in dynamic programming, we were essentially able to evaluate exactly these expectations through the use of the transition dynamics. Right? And so we weren't really defining these estimates of these expectations because we could actually compute the exact expectation by basically analyzing this, basically computing this expectation analytically through the knowledge of the dynamics. Any questions here? Okay, so we've seen now how we introduced these two basically techniques, right? So we discussed sampling as essentially our mechanism to approximate expectations through interactions with the environment. And we saw how both Monte Carlo and TD learning sample. And this is because they're model-free algorithms. So we assume we don't have knowledge to the dynamics. On the other hand, dynamic programming does not sample, because there we assume we had knowledge of the dynamics and we could compute those expectations exactly. We then discussed also bootstrapping, where the idea is to basically update our guess towards a guess, right? And we saw how both TD learning and dynamic programming were using this idea, while Monte Carlo did not. And so really what we're doing today is basically constructing or paving a unifying view of all possible reinforcement learning algorithms, depending on these two axes. So, and specifically thinking about these trees that we were observing before, different algorithms fall on a spectrum depending on the width of the backup. So we discussed algorithms that look at the full width of the backup, that is dynamic programming, or intuitively also exhaustive search. Right? We could just sample infinitely until we explore the full tree. Or on the other hand, algorithms that only use at the extreme one sample from the environment, right? And so we looked at temporal difference learning and Monte Carlo learning. Similarly, we looked at the height of the backup, that is through, on one extreme, Monte Carlo and exhaustive search require reaching the end, so a terminal state, in order to update their values. And TD learning and dynamic programming instead relied only on a one-step update because they could use bootstrapping to approximate their values. Of course, these are just kind of four extremes of a spectrum, and you could envision algorithms laying somewhere in between, right? So for example, you could assume having, rather than updating your to the target after one step, you might assume that you want to do 4 steps of experience and then use the value function after 4 steps of experience. And there are pros and cons when doing so. Okay, so let's now build towards, if you want, a first working version of a reinforcement learning algorithm using these tools. So in previous lectures, we introduced policy iteration, and also earlier today. And we essentially discussed how this is an algorithm that implements 2 interactive processes, right? We have policy evaluation on one hand, which, given a policy, estimates the value for that policy. And then we have policy improvement, where, given a new estimate of the value function, we used it to improve the correct policy. In general, we will use the term generalized policy iteration to refer to this general idea of an algorithm skeleton or structure, whereby we will be iterating between these 2 processes, regardless of how these 2 processes are actually specifically defined. In policy iteration, we saw how the policy evaluation scheme, the policy evaluation step, was essentially iterative enforcement of the Bellman expectation equation. And for the policy improvement step, we used a greedy policy improvement, right? So we were taking the argmax over the quantity defined by the new value function. But this is a general formalism, and you will see how many algorithms actually apply this skeleton. Okay, so we mentioned how policy iteration specifically required knowledge of the dynamics in both of these processes, right? So we used the knowledge of the dynamics to perform policy evaluation through the Bellman expectation equation, and we used the knowledge of the dynamics to improve the policy in our greedy improvement step. So can we make this actionable through everything that we learned today? So the first thing that you might think of is, can we replace the analytical policy kind of Bellman expectation equation through Monte Carlo policy evaluation of the value function? Right? So the first step is we were given a policy and we want to estimate the value for that policy. Can we do this through Monte Carlo policy evaluation, which is what we've done today? And potentially leave unchanged the greedy policy improvement. And the answer is that, well, yes, in the sense that Monte Carlo policy evaluation will work, and this is exactly what we've been doing today in both in the Monte Carlo learning section. But then the greedy policy improvement, as we said before, relied on this knowledge of the transition dynamics to update our policy, to take this argmax, right? So this will not cut it in a way. So kind of one thing is that, so we discussed before how the Q function is a nice object in order to, and a convenient object in order to define a policy implicitly. So let us just replace the value function v with the Q function. So now we're looking at a version of policy iteration where we are doing Monte Carlo policy evaluation of the Q function and then potentially greedy improvement. So will this work? What do you think? Well, there is a spoiler on the slides, of course, but what do you think and why? Well, the point is that it won't in general. And the idea is that here it kind of touches on, I would say, a really fundamental issue and challenge in reinforcement learning, which is the one of exploration. So the trade-off between exploitation and exploration. So let us look at this from the perspective of a simple example. So say we have two doors, and we need to pick among these two doors, and each of these two doors will give us a specific reward. This is, in a way, stateless environment because we are always in the same state, right? So we have nothing that conditions us in picking the two doors. But now, say that we have no information of the quality of the two doors, and that we, first of all, so we initialize our Q function randomly, and then also randomly we basically pick the left door as our first interaction. And we get a reward of 0. So we basically update the value of our Q function as 0. Now we similarly kind of execute in our environment, and we pick the right door. And we observe a reward of 1 in this case. So we update the value of the Q. Now note that in general, right now the policy that we are executing in the environment is a deterministic policy, right? It is the argmax over the Q function. So since we have basically created the situation where the right choice is basically dominating the left door, here and basically forever, we will always be choosing the right door, right? And so this is potentially at loss of a better reward that we might have had on the left door. And so the problem here is once we estimate Q functions or state action values through samples, then we need to visit every state action pair in order to approximate those values. And deterministic policies do not allow for this exploration. So a simple but effective trick and strategy is to basically introduce some randomness in how we explore the environment, in how we take decisions. And a simple strategy is the one of epsilon greedy exploration. Specifically, with some probability epsilon, 1 minus epsilon, we will be consistent with how we picked the action so far. So we will just take the argmax over Q. On the other hand, with some small probability epsilon, we will be acting random. So we'll just pick random actions from our possible action space. This is a very simple trick, but fundamentally this ensures that all M actions are tried non-zero probability. And so this, on the long run, ensures that we are visiting and exploring, and that is having a nice coverage of our entire state action space. And so if you wish, kind of this builds and leads us to kind of a first working version of a reinforcement learning algorithm. That is something where we have Monte Carlo policy evaluation of a Q function, and then an epsilon greedy policy improvement. So since the goal for today is becoming experts at blackjack, let's look at how, like, the policy that we will get if we run this in practice on the same environment that we had before. So now, before we were focusing on policy evaluation. So we were given a specific policy that was standing if the sum of cards was 20 or above. Now we're actually doing the full problem where we actually want to derive an optimal policy for the task. And so here, kind of, if you trust me, that by running exactly the algorithm that we discussed so far, we would basically be converging to this policy over here, whereby we have a specific rule that we can also inspect, where depending on if we have a usable ace or not, and kind of the sum of the cards and the dealer's showing card, we have an explicit rule of whether to stick or stand or hit. And note, maybe intuitively, that if we don't have a usable ace, we're actually more conservative here, right? So of course we can go into the details, and I'm definitely not advising you to try this strategy if you go in casinos. But this is the idea, right? Again, we gave no clue, no intuition whatsoever to the environment on how to behave, and through this interaction, we derived both an optimal policy and its respective value function. Okay, so to recap what we've been discussing so far. So we started from exact methods for solving Markov decision processes, right? Namely policy iteration and value iteration. And we said and recognized that these have some limitations. Specifically today, we looked at the first of these two, which is the one that in both the update equations and in the of our estimates for the value function, that is the Bellman equations, And in the greedy policy improvement steps, we were using implicitly a knowledge of the transition dynamics. And so today, we focus on these two main classes of methods and families of methods, MC learning and TD learning, to address this through interaction. And so indeed, we introduce MC learning and TD learning as examples of a spectrum, right? Where depending on the height or width of the backup, we could derive different algorithms, all under the shared goal of solving unknown MDPs through learning. We did not discuss how we could deal with high-dimensional state action spaces, but we'll do this in the coming lectures. Okay, any questions here before I spend a few minutes on some concluding remarks? All right. So if you recall, last week we were looking at this taxonomy of reinforcement learning algorithms. Starting next week, we'll be looking at, in order, we'll be looking at value-based methods next Monday. We'll then be looking at policy optimization next Wednesday. And then we'll be looking at model-based algorithms. Well, not next Monday because that's bank holiday, but next time. And then we'll be looking at model-based algorithms. In general, I think it is really valuable to see all of these algorithms as different instantiations of a common shared skeleton of our reinforcement learning algorithm. And specifically, the skeleton has three main processes going on. The first one is that all algorithms will have some way of generating samples, right? Because we want to learn from interaction. And as we saw today, interaction for us essentially means sampling episodes from interactions with the environment, where the goal here will be essentially to collect these trajectories or episodes of interactions tau, and use these quantities to basically do something with it. Specifically, we'll use these samples from the environment to either fit a model or estimate a return or a value. Right, so today we discussed extensively how we might be interested in estimating value functions or Q functions. But in general, we might also see how we could use these trajectories to estimate a learned model of our dynamics in model FRL. Bottom line is we will have some interactions with that environment, and we'll be doing something with that interaction, which is loosely speaking either estimating some values or fitting some model of our dynamics. And then we'll use these computations that we do in the second block to improve the policy. Today, we saw how we are basically using an epsilon greedy or greedy policy improvement step, but we will see different ways of improving the policy. For example, we'll see how in policy optimization algorithms, we will be taking gradient steps with respect to some parameters theta, which might represent a parametric policy that we're defining in order to optimize the RL objective directly, that is maximize estimated return. But we'll see this more next week. Okay, but bottom line is, I think this is a very useful mental model to use when approaching different RL algorithms, because this is really at their core what most of these are doing. Okay, so if there are no more questions, I'll see you next time with value-based reinforcement learning. Thank you.